In our last lesson, we looked at acids and bases the way a chemistry student would look at it who's already had some experience with acids and bases in earlier classes. The perspective of a high school student looking at acids and bases who might know how acids are named but didn't know much about the way they behave. Well, now we're going to continue that exploration. We started out with a pH wheel, I call it, but we didn't finish the top of it. So in this lesson, we'll finish it. In the previous unit, we learned to calculate molarity. We've established the relationship between the molar concentration of a strong monoprotic acid and the molar concentration of hydrogen ions. We've learned to calculate pH. We've learned to calculate the molar concentration of hydrogen ions from the pH, although we didn't use it on the most recent work. We did it as a practice. We learned to calculate the pOH from pH. That same equation can be used to calculate pH if you know the pOH. We learned from the from the pOH how to calculate the molar concentration of the hydroxide ion. And of course, all these can be used to go in both directions. And I like to call this the pH wheel. Okay? And so if we were to look at it as if the pH is here, then from pH we can calculate the molar concentration of hydrogen ions, and we'll get to what this H3O plus means a little later. Or we can calculate using this calculation down here at the bottom, this equation down at the bottom, what the pOH is. So from pH, then we can get to pOH using that. From pOH, then we can also get to the molar concentration of the hydroxide ion. All right, now that I fixed that little notation error, from both these places then, we're able to get to hydrogen ion concentration, and from that we're going to be able to get to this other thing we're going to talk about today, and then from a hydroxide ion concentration we get the same way, same place. So this is why I call it the pH wheel, because you can go in either direction. You can start from any one of these values and go in either direction to get all the others. Okay, what we haven't spoken about yet is what's at the top of the wheel here. And that's what Kw is and what this equation means. Okay? As it turns out, though, that equation at the top of the wheel is the place from which we get the equation at the bottom of the wheel. Okay? And we're going to talk about that now. And then we'll talk about how to do the math. So, what is Kw? So the capital letter K is a symbol we use in chemistry for a sort of an important or combined constant for things. Okay, little letter K is a constant for a specific circumstance. Capital letter K is like a constant that is almost universal. I wouldn't say it's completely universal, but it's kind of has much bigger applications than a little letter K. So this applies to water at around room temperature, about 22 degrees C. Okay, so in water, I know you've heard somebody talk about, oh, it's pure water, but there's really no such thing as pure water if you think of water being water molecules, H2O. It turns out that in any sample of water at about effect is greater when the water is hotter than when it's colder, but at around 20 degrees C, there's a certain percentage that's well known of water molecules that dissociate. So we talked about what dissociate means yesterday. That's a term we use for ions or ionic compounds when they break apart in water to form those separate ions. It's a term we use for acids when acids break apart in water and form those separate ions. When we're talking about acids, and we're specifically interested with acids and how the hydrogen are breaking off, we talked yesterday about how that hydrogen is really a proton. So often, instead of using the word disassociation or dissociation for acids, we'll call it deprotonization. That really only refers to removing the hydrogen ion and not splitting it so much. I mean, it really comes down to be the same thing, but since we're more interested in the protons or hydrogen ions, we'll call it deprotonization. Well, both terms will work here because water is deprotonating and it's also dissociating, okay? So in a sample of water, there's always a very tiny amount of water molecules that go through dissociation. Okay, so if we're at 20 degrees C, and this is a reversible reaction, okay? It's going both ways, okay? There's an equilibrium here. At equilibrium, at 20 degrees C, we know what the concentration of hydrogen ions is. If I have a liter of water that's as pure as I can get it to be, and it's at 20 degrees C, an equilibrium is established where water molecules, a certain number of them, are breaking apart, and we get, let me think now, okay, it's 1 times 10 to the negative 7 moles per liter of water. Okay, so that's a very small number. That's like 0 point and then 6 zeros before you get to the 7, a very small number of water molecules that are breaking up. Well, that means that they came from 1.0 times 10 to the negative 7 moles per liter of water. Okay, there's a lot more water molecules in a liter. Okay, a lot more moles in there than that. Okay, this was a much bigger, a really huge number compared to that. All right, well, if we get one of these, as we looked at yesterday when we looked at the math for splitting up a monoprotic acid, if this is 1.0 times 10 to the negative 7, this is also 1.0 times 10 to the negative 7 moles per liter, and moles per liter just means that it's molarity. Okay. In pure water, that's a value we know about. We can depend on that. But there is an equilibrium going on here. All right. Remember that an equilibrium comes from a reversible reaction. If I change something on this side, it's going to change the balance to get this side to change. Okay. Well, that number is so huge that we almost always ignore that. But the result of that balance, that equilibrium, is that if I change the number of hydrogen ions, say by adding an acid, then that's going to cause the number of hydroxide ions to shrink. Okay? And the value of all that is the Kw. Okay? Kw is 1.0 times 10 to the negative 14. And that's this number times this number. Okay? So this Kw is the molar concentration of hydrogen ions times the molar concentration of hydroxide ions. Now, if that only applied to pure water and no other situation, then it wouldn't be a constant. But it's a constant because if I increase the molar concentration of hydrogen ions, the molar concentration of hydroxide ions will decrease to keep it constant. Okay? And that's why it's so valuable. So you see that 14 right there? And earlier I said that this equation is where we get, where we derive that 14 equals pH plus POH. That's the number right there. Okay? So, that being the case then, we know that in pure water, 1.0 is kind of a rounded off number. It could be 1.000. Okay? So you can say 1.00 or 1.000, whatever, okay? So we're not going to use this number for figuring out significant digits, okay? Now, is times 10 to the negative 14 is equal to the molar concentration of hydrogen ions times the molar concentration of hydroxide ions, okay? Remember, moles per liter is molarity. So this number could also be written 1.0 times 10 to the negative 7 molarity. 1.0 times 10 to the negative 7 molarity, or molar concentration, okay? And molar concentration times molar concentration is molar concentration squared, right? Just like x times x is x squared, or y times y is y squared, right? Okay, so the actual value of this is molar concentration squared. Okay, so this number does have a unit. Well, that's what goes at the top then of that pH wheel. And so, if we take the values we had from our homework problem, and we found at the end of the homework problem that we had a molar concentration of hydroxide ions equal to 1.73 times 10 to the negative 12 molar, I can plug this number into this equation and find the hydrogen ion concentration. Okay, so let's pause the video and let you guys do that now. Okay, plug it in the into the equation. This is just like solving Boyles Law problems and gas laws. Okay, the math is the same. All right, so plug this number in for the molar concentration of hydroxide ions and see what the hydrogen ion concentration comes out to be. Okay. All right, so you gotta set it up like this, where you put this number in here, and you're plugging in the value we had for the molar concentration of hydroxide ions here for that number, and then you're going to divide both sides by this number in order to isolate the unknown. That's what we talked about when we're doing gas laws and doing calculations with Boyles Law. Now, when I divide molar squared by molar, that's like molar times molar, and it cancels out one of the molar units. Okay, y'all know how that works, like x squared divided by x is just x, right? Okay, so now I've been asked to show you how to do this math using just a basic calculator, something like this, okay? Now, do you have parentheses on the calculator you're talking about? Okay, so I'm going to open a parentheses. I'm going to put in 1.0, and let's see here. Do I have an E? Or here's a double E right there. So second double E, and that would be negative 14. So I'm hitting the change of sign button for that negative 14. Negative 14. Close the parentheses. Divided by, open a parentheses for what's on the bottom, 1.73, and then put in the double E is like that exponent or E on the calculator screen. All right, or times 10 to the some number is what that double E is for. So times E or double E, and then negative 12, and close my parentheses. Okay, and hit equals, and I get this number here. Okay, got that? Oh, and guess what? Comes really close to our original value, right? There it is. That's what I expect. That's what you would expect to get. If you go all the way around the wheel and come back to where you started from, that's what you would expect to get. So, looking at our, well, let's bring it up here if I can get it to come up here. Here we go. Our wheel. So we started with pH, and we worked our way all the way back around till we got to here. Okay. Got it?
Yes.
All right. Do you want me to show this to you on any other calculator?
No.
No, that's good.
You used one yesterday that looked like this.
Oh, an inexpensive one of the inexpensive calculators. Oh, gracious. All right, so here's a practice problem for you. If 1 gram of HCl is dissolved in 900 milliliters of aqueous solution. What are the hydrogen ion molar concentration, the hydroxide ion molar concentration, the pH, and the pOH? All right, does everybody see what I've done here? I've justified the claim that the molar concentration of HCl is going to equal the molar concentration of hydrogen ions by stating that HCl is a strong monoprotic acid here, okay? So that whenever I write down here that this molar concentration is also this molar concentration, I have a reason to justify that answer, okay? All right, so I put the 1 gram of HCl over 1, calculated the molar mass here. I used that equality statement at the end of my calculation for molar mass to build this conversion unit so I could get to moles. Then I put the 900 milliliters of HCl solution on the bottom, converted that to liters here. Here's the equality statement to justify that conversion. And I get a molar concentration of H plus of 0.0305 molar. Okay? Then from that, I'm going to calculate the molar concentration of hydroxide. Now you could have gone around the wheel in the other direction and gotten there, but I chose to go directly based on the order the question asked for them. I said that the B part of the second question was to find the hydroxide ion concentration. So I used this equation, the one we just learned, Kw, the autoionization. By the way, the name of that, I don't know if I told you this, Kw stands for or means the autoionization constant for water. Or you could also say the dissociation constant for water. Okay? But it's a constant, and you have to say what that means. The subscript W means that it applies to water. And so far as I know, that's the only constant of this type that applies to water. Okay? So the autoionization constant for water equals the molar concentration of hydrogen ions times the molar concentration of hydroxide ions. And I put in the values. Here's the Kw value. Here's the molar concentration of hydrogen ions from there. And I just divide both sides by that value in order to get hydroxide ion concentration by itself and calculate this number. Then to find the pH, because that was the third thing the problem asked for, I'm doing it in the order it asked for it here. To find the pH, I took the molar concentration of hydrogen ions and took the negative log to find a pH of 1.516. Then since pOH was the fourth thing, I'm using this equation. And I plugged in the pH value here. I subtracted that value from both sides, and I get 12.484 is the pOH. Okay? Now, like I said, you could have calculated it going in a different direction around the pH wheel. You could have avoided using this equation at all if you wanted to. And I would accept your answers if your math justifies it. Okay? Everybody clear with that? All right. So, we've done all these calculations really already, except for this is the only one we've added today. Okay, we've done talk about the theory of where we could get it from and such. Before we leave today, I want to talk about a couple of things. Let's go back to that pH wheel for a second. All right. So, hold on, something isn't quite right here. All right. So, we have this H3O plus plugged in here. We have it plugged in right down here as well. Okay. I want to talk about where we get those from. Okay. Thus far, every time we've talked about the way that acids behave, we've used what's called the Arrhenius theory. Okay. And in the Arrhenius theory, if I were to use, let's use Ha as our general symbol for all acids, okay? Because all acids are going to have hydrogen on the front and will have an anion. If this is hydrochloric acid, A is Cl. If this is hydrobromic acid, A is Br. If this is hydroiodic acid, A is I. The A here just stands for all anions, okay? So if I'm using an Arrhenius theory, then I get this, all right, when I dissociate or I deprotonate. If I'm using what's called a Bronsted-Lowry theory, the Arrhenius theory says that acids produce a hydrogen ion, or acids give away a hydrogen ion to water. Bronsted-Lowry, this is two different names, two different people. Bronsted and Lowry, they did this. They basically came up with the same answer in two different places at about the same time. So they give the name to this process or theory to both of them. So it's Bronsted-Lowry. Lowry's English, Bronsted's Danish, I think it is. Okay. So what happens is with Bronsted-Lowry is the theory of acids is that acids donate a proton to some other chemical species. So with this theory then, the hydrogen doesn't just break away. It actually joins up with a water molecule. So the H joins up with the water molecule and we get something called hydronium. We still get that anion over here, okay? If we were looking at this with Lewis dots, remember Lewis dots? Okay, water has, or the oxygen in water has two lone pairs. Okay, so this hydrogen from the acid, when it breaks loose, what it actually, so this is the Arrhenius part of the theory. This hydrogen actually goes over here and joins up with one of the lone pairs on the oxygen on the water, and what you end up with is this. And then you also have that anion, okay? So that's where that H3O comes from. We'll talk about Bronsted-Lowry and Arrhenius theories a little more detail later. We're only going to briefly talk about the Lewis theory for acids and bases, which deals with these electron dots as well. Okay? Everybody got all that?
Yes, sir.
All right, so that's where we get that H3O is. Now, if this is the case here, then for every hydrogen ion that breaks off here, we're going to make one H3O. So the same way we did the math yesterday for figuring out how many H3Os there are, the number of hydrogen ions in the Arrhenius theory is equal to the number of hydronium ions in the Bronsted-Lowry theory. Okay? So sometimes we'll say that pH then is the negative logarithm of the hydronium ion. Okay, in the Bronsted-Lowry system or way of thinking about things. Let's talk about strong acids and weak acids briefly, okay? So far we've identified three strong acids: hydrochloric, hydrobromic, and hydroiodic. But there are 7 strong acids, and you need to know all 7 of these, okay? Hydroiodic we talked about, hydrobromic we talked about, hydrochloric we already talked about, okay? So you should pretty much be familiar with those 3. In addition to those 3, nitric acid is one of the strong acids, chloric acid is one of the strong acids, and perchloric acid is one of the strong acids. All 6 of these are monoprotic. Notice they all have just one hydrogen. So all the math we've been doing so far for strong monoprotic acids, we could also use nitric, chloric, and perchloric for any of those kind of calculations because they are also strong and monoprotic. Okay, there is only one strong acid that has more than one proton, and that's sulfuric acid. Only one polyprotic acid that's strong. Let's back that up a minute. There are others. There's only one common, okay? This is the only one you have to worry about. Sulfuric acid is the most common industrial acid in the world. Because when we burn coal, and we burn a lot of coal to make a lot of power in the United States, it gives off a lot of sulfur. That sulfur is captured in the smokestacks, and that sulfur then is turned into sulfuric acid. So there's a lot of sulfuric acid around. Okay? Everybody got that? All right. 6 strong monoprotic acids, 1 strong polyprotic acid. Okay? There are 4 strong bases. Now that depends on who's defining what strong bases are. These are the 4 I want you to know about. Some people would define strong bases slightly differently and would have a different one in the list, or would add one more to the list, or whatever. But these are pretty commonly considered strong bases. Now what that means is it's the same reason why acids are strong. Acids are strong because they completely dissociate. Bases are also strong because they completely dissociate. Okay? Let's talk about weak acids. And I'm going to use a colloquial southern term here. If it ain't on the list, it's weak. Got it? That's also true for weak bases. If it ain't on the list, it's weak. Okay? We're in South Carolina, we can say that, right? All right. Let's talk about just a couple of other acids real quick before we give you a homework problem. Okay? There are 2 acids that I want you to know about that help to maintain your blood pH. These are weak acids, and they have a buffering system, which we will talk about next week. Okay, what buffers are and how that works. So the reason that in that lab we did earlier this week, where we had to add so much more base to neutralize a weak acid, is because weak acids all are buffers. All right. So the 2 acids that buffer the pH in your blood are phosphoric and carbonic.